there you, ready to dive into a chemistry lab for the first time in a while? Or maybe ever. Don't worry, we've got you covered. This deep dive is all about getting comfortable with the essential equipment and techniques. Perfect for anyone brushing up on their chemistry basics. We're about to unravel the mysteries of beakers, burettes, and all those weird-looking flasks. Ready to get started?
Absolutely. And it's important to remember, you can't just waltz into a chemistry lab and start mixing things willy-nilly. You need to understand the tools of the trade.
Okay, let's unpack this. First, we're talking glassware. Imagine you're walking into a lab and your eyes are drawn to all these glass containers. They're not just for show, you know. Each one has a specific purpose, and it's worth knowing what they are. So let's start with the most iconic piece of lab equipment, the beaker. It's like the measuring cup of the chemistry world, right? Great for mixing, heating, and stirring solutions.
Exactly. And the thing to remember is that beakers aren't meant for super precise measurements. They're more like a general guide. Imagine trying to bake a cake using a beaker to measure the ingredients. You might end up with something edible, but it probably wouldn't be pretty.
Which brings us to the next level up, graduated cylinders. Now we're talking about precision. You've got those graduated markings on the side, which means you can be much more specific about the volume you're using. And of course, you need to be careful about reading that meniscus correctly, the bottom of the curve, not the top.
Yes, the meniscus is key. It's a bit of a detail that some people overlook, but it makes a big difference in the accuracy of your measurement.
Okay, here's where it gets really interesting. You've got your beakers and your graduated cylinders, but sometimes those aren't quite enough. You're going to see these funky shaped flasks like the Erlenmeyer flask. I mean, why is it shaped like that? It's not just for looks. It's actually designed for swirling and mixing solutions without spilling all over the place.
Exactly. The narrow neck helps prevent accidental splashes, which is important when you're working with chemicals. Think of it like a funnel for your experiments.
Speaking of flasks, you also have the boiling flask. That one is a bit more, well, round, and it's designed for heating liquids. But it's important to remember that just like the Erlenmeyer flask, the boiling flask isn't the best choice for measuring volumes.
That's right. The round bottom means it's a bit wobbly, and you need a clamp to keep it upright. It's more about heat and swirling than precise measurement.
So if you need to be really precise about your solutions, then you're going to need a volumetric flask. These are designed to hold one very specific volume, and there's a little marking on the neck that tells you exactly how much to fill it up. Think of it as the top-of-the-line precision tool in your glassware arsenal. And then there are droppers. They're tiny but mighty, perfect for adding those indicator solutions drop by drop so you can really fine-tune your experiments. Now, the burette. This is the star of the titration show. It's that long, graduated tube with a stopcock at the bottom, which lets you release the titrant drop by drop.
That's right. Burettes are all about control. You can release the titrant in very precise amounts, which is essential for titrations.
Speaking of precision, what's the difference between volumetric glassware and graduated glassware? I feel like we've been throwing that around, but it's time for a little clarification.
Good point. Volumetric refers to glassware that has a single marking for a specific volume, like the volumetric flask. These are generally more precise because they're designed to measure one volume accurately. Graduated glassware, like the graduated cylinder, has multiple markings for different volumes. It's still useful for measurements, but it's not quite as precise as volumetric glassware. You think of it like this. Pipettes are the most precise, then burettes and volumetric flasks, then graduated cylinders, and finally the least precise are beakers and Erlenmeyer flasks.
So what does this all mean? Say you're working on an experiment and you need to measure out exactly 5.0 millit of liquid. What would you use?
Definitely a burette. It's the most precise option for that kind of measurement. You wouldn't want to rely on a beaker or even a graduated cylinder for that level of accuracy.
Exactly. It's all about choosing the right tools for the job. We've just scratched the surface of the lab equipment, but we've already got some key concepts under our belts. So now that we've covered some of the essentials, let's shift gears and talk about those lab techniques. You can have all the best equipment in the world, but if you don't know how to use it, it's not going to do you much good, right?
Absolutely. Technique is just as important as the tools themselves. And that's what we're going to tackle next, how to actually use all this fancy glassware.
Exactly. So let's start with something basic but crucial, measuring mass. We've got those digital balances, but there's a little button on there that often gets overlooked, the tare button. I'll admit I've definitely been guilty of just placing the weighing paper directly on the balance pan. Why is the tare button so important?
Ah, the tare button. It's the unsung hero of accurate measurements. You see, you never want to put your sample directly on the balance pan. It can contaminate the pan or even damage it. Think of it like this. If you were trying to weigh yourself on a scale, but you were still wearing your shoes and a heavy coat, the reading wouldn't be accurate, right?
That makes sense. So the tare button is like hitting reset to zero out the weight of the container, so you're only measuring what's inside.
Precisely.
Now, what about when you need to separate solids from liquids? That's where things get a little more, shall we say, spinny.
You're talking about centrifugation. Picture this. You have a mixture of sand and water, and you want to separate them. You could try to carefully pour off the water, but you'd never get all the sand out. That's where a centrifuge comes in. It spins the mixture at incredibly high speeds, creating a force that pulls the denser particles, in this case the sand, outward toward the bottom of the tube.
Right. It's amazing how such a simple concept spinning can be so powerful in the lab. Speaking of powerful, let's talk about titration. We've already touched on the burette, but now it's time to see it in action. It sounds so precise, like a chemist's version of a super slow controlled pour.
Titration is all about precision and control. Imagine you're trying to neutralize an unknown acid solution, like figuring out exactly how much baking soda you need to counteract that overly vinegary salad dressing. In titration, you slowly add a solution of known concentration, your titrant, like the baking soda, to the unknown solution, the salad dressing.
So you're carefully adding one solution to the other, drop by drop, until something happens.
Exactly. You're looking for the equivalence point, that magical moment when the reaction is complete. It's like finding the perfect balance. And to help visualize this, we often use an indicator, a substance that dramatically changes color at the equivalence point. It's like a visual cue that shouts, "Eureka, you've reached the perfect balance."
I'm starting to see why this technique is so important. It's about finding that sweet spot, that perfect balance. Now let's talk about heat, specifically how we measure those heat changes during chemical reactions. Calorimetry. I'll admit, it sounds a bit intimidating, but I have a feeling you're going to break it down for us.
Of course. Calorimetry is essentially the study of heat transfer. Think about what happens when you add a hot piece of metal to a cup of cold water. The metal cools down and the water heats up, right? Calorimetry helps us quantify that heat exchange.
So instead of just observing that something got hotter or colder, we can actually measure how much heat was transferred. What's the go-to tool for this in the lab?
In a basic chemistry lab, you'll often use a styrofoam cup calorimeter. It's low-tech, but it gets the job done. It works because styrofoam is a great insulator. It helps to trap the heat inside the cup so we can measure those temperature changes accurately.
Wow, so even something as simple as a styrofoam cup has a place in a chemistry lab. So we've got our reaction happening inside this insulated cup. And what, we just stick a thermometer in there and watch the temperature change?
Exactly. By measuring the temperature change of the reaction mixture, we can determine whether the reaction released heat, exothermic, or absorbed heat, endothermic.
So those seemingly simple temperature changes are giving us valuable clues about what's happening at the molecular level. I'm starting to think like a chemist, looking for clues everywhere.
Yeah, the spirit.
We've covered a lot of ground here, measuring mass, separating mixtures, titration, and even calorimetry. It feels like we're well on our way to becoming lab pros.
We're getting there. But before we get too carried away, there's one more crucial aspect of working in a chemistry lab that we need to address: safety. It might not be the most glamorous topic, but it's arguably the most important. You can never be too careful when working with chemicals.
You are absolutely right. We can't just be mixing and swirling things without considering the potential hazards. Safety isn't just about following rules, it's about protecting ourselves and those around us.
Exactly. It's about understanding the potential risks and taking the necessary precautions. So let's dive into some essential safety protocols. Imagine this, you're in the lab, and suddenly, disaster strikes. You accidentally spill a bit of acid on yourself.
Okay, that's definitely my nightmare. But hopefully I'd remember what you said earlier about not panicking. What's the first line of defense in a situation like that?
That's when those safety heroes we talked about earlier come into play. The safety shower and the eye wash station. They're like your emergency reset buttons in the lab. A quick drench in the safety shower can wash away any chemical spills and minimize the risk of serious injury.
It's like a superpower that instantly washes away any chemical mishaps. I'm feeling safer already.
And speaking of protection, let's not forget about those other unsung heroes, fume hoods. Those chemical reactions can sometimes come with, shall we say, interesting aromas.
And by interesting, you mean potentially hazardous.
Precisely. Fume hoods act like giant exhaust fans. whisking those fumes away and keeping the air in the lab safe to breathe.
It's like they're saying, hey, I'll take that noxious cloud for you. You can thank me later. Now, what about fire? Fire extinguishers seem pretty self-explanatory, but I have a feeling there's more to it than just pointing and spraying.
You're right. It's crucial to know what kind of fire extinguisher to use and how to use it properly. There are different types for different kinds of fires.
Yeah.
Some are designed for flammable liquids, others for electrical fires, and so on.
So it's not a one-size-fits-all situation.
Exactly. Using the wrong type of extinguisher can actually make things worse. And just as important as knowing how to use a fire extinguisher is knowing when not to use one. Some fires require specialized equipment, and it's best to leave those to the experts.
Got it. When in doubt, it's probably best to evacuate and call for help. Better safe than sorry. Okay, so we know where the safety equipment is, but what about protecting ourselves before anything even happens? What can we do to minimize the risks from the get-go?
That's where personal protective equipment comes in. Your PPE. We're talking lab coats, safety goggles, gloves, the whole 9 yards.
Like a chemist's version of a superhero suit?
Exactly. This isn't just about following the rules, it's about creating a barrier between you and potential hazards.
Right. It's like putting on armor before heading into battle. A chemistry battle, that is. You wouldn't fight a dragon without your shield, and you shouldn't handle chemicals without your safety goggles.
Exactly. And while we're on the topic of protection, let's not forget about proper disposal. We can't just pour everything down the drain when we're done with it.
Good point. It's not like cleaning up after baking. We can't just dump everything in the sink and call it a day.
Exactly. Some chemicals can be safely washed down the drain with plenty of water, but others require special handling. It's all about knowing the properties of the substances you're working with and disposing of them responsibly.
Absolutely. And on that note, let's talk about something that should be common sense but bears repeating. No eating or drinking in the lab. This isn't a picnic. It's a place where precision and safety are paramount.
I can't stress this enough. Imagine accidentally grabbing a beaker that you thought was filled with juice, but actually contains a strong acid.
Okay, that's a recipe for disaster. I think I'll stick to my designated snack breaks, far, far away from any potential chemical spills.
A wise decision. And speaking of avoiding unnecessary risks, let's talk about adding water to acid. It sounds harmless enough, but I have a feeling there's a reason it's a big no-no in the lab.
You're right to be cautious. Remember those exothermic reactions we talked about?
Exactly. Adding water to a concentrated acid can generate a lot of heat very quickly. It can cause the solution to splash or even boil violently, potentially spraying hazardous material everywhere.
It's like the chemistry version of adding fuel to a fire. Definitely not something you want to experiment with.
Precisely. The key takeaway here is to always add acid to water, slowly and carefully, stirring constantly. It's all about controlling the reaction and minimizing the risk.
Got it. Acid to water, like A to W. Always work my way down the alphabet in the lab. Speaking of minimizing risk, I'm starting to feel a lot more confident about tackling those chemistry experiments safely.
That's what we like to hear.
Yeah.
And on that note, let's move on to the final, and some might say the most important part of our chemistry lab crash course: data and error analysis.
Because what good are all these experiments if we can't make sense of the results, right? It's like meticulously following a recipe, but then forgetting to taste test and adjust the seasoning at the end.
Exactly. Data analysis is where we turn those raw numbers into meaningful conclusions. It's where we separate the signal from the noise and figure out what our experiments are really telling us.
And let's be real, no measurement is perfect. Even with the most precise equipment and techniques, there are always going to be little variations of uncertainties.
You're absolutely right, and that's where error analysis comes in. It's not about being perfect. It's about understanding and accounting for those inevitable errors that can creep into our experiments.
So it's about embracing the imperfections and figuring out how they might influence our results.
Precisely. We want to be as accurate and precise as possible, but we also need to acknowledge the limitations of our measurements. It's about being honest with ourselves, about the uncertainty inherent in any scientific endeavor.
That makes a lot of sense. So how do we even begin to grapple with these errors? I imagine there's more than one way to mess up an experiment.
You're right, there are many sources of error, but we generally categorize them as either systematic or random.
Systematic versus random errors. That sounds intriguing. Tell me more.
Systematic errors are those pesky biases that can sneak into our measurements, often without us even realizing it. They can stem from flaws in our equipment, like a balance that's slightly off, or from inconsistencies in our procedures.
So it's like having a measuring cup that's always a little bit overfilled. Every measurement you take with it is going to be slightly off, even if you're super careful.
Exactly. And the tricky thing about systematic errors is that they tend to skew our results in one direction, either higher or lower than the true value. It's like trying to hit a bullseye with a dart that's always veering off to the left. You might be able to adjust your aim somewhat, but you're never going to hit the center consistently.
That makes sense. Okay, so systematic errors are all about those consistent biases that can throw off our results. What about random errors? Are they as sneaky and pervasive?
Random errors are those unpredictable fluctuations in our measurements that are often beyond our control. They can be caused by a whole host of factors, from slight variations in temperature or humidity to limitations in our own perception.
So it's like those tiny tremors in the ground that you don't even notice unless you have a super sensitive seismograph.
Exactly. And just like those tiny tremors, random errors are often unavoidable. But the good news is that we can minimize their impact by taking multiple measurements and using statistical analysis.
So it's like the old adage, measure twice, cut once. By taking multiple measurements, we're essentially hedging our bets and reducing the chances of a single random error skewing our results.
Precisely. And statistical analysis gives us powerful tools to quantify that uncertainty and determine how confident we can be in our conclusions.
It's like having a whole arsenal of mathematical techniques to help us separate the wheat from the chaff, so to speak.
Exactly. And speaking of separating the wheat from the chaff, let's talk about significant figures. These aren't just random digits. They tell us something about the precision of our measurements.
It's like saying, hey, I'm only confident about these digits, the rest are just noise.
Exactly. If you tell me you measured 10 milliliters of a solution, it doesn't tell me as much as saying you measured 1000 milliliters. Those extra zeros imply a much higher level of precision.
So those seemingly insignificant figures are actually sending a powerful message about the accuracy of our measurements.
Precisely. And when we start doing calculations with those measurements, those significant figures matter. We need to make sure we're not claiming more precision than our measurements actually justify.
It's like building a tower of blocks. The foundation needs to be solid, or the whole thing will come crashing down.
Exactly. And speaking of solid foundations, let's circle back to the difference between accuracy and precision. These two concepts often get confused, but they're essential for understanding and interpreting our data.
Right. They sound similar, but I have a feeling they have distinct meanings in the world of chemistry.
You're absolutely right. Think of it like this. Imagine you're throwing darts at a dartboard. Accuracy is how close your darts are to the bullseye. Precision is how close they are to each other.
So you could have a cluster of darts that are all very close together, very precise,
Yeah,
but if they're nowhere near the bullseye, then they're not very accurate, right? It's like you have a steady hand, but your aim is off.
exactly. And in the lab, we ideally want both accuracy and precision. We want our measurements to be close to the true value and reproducible.
So it's not enough to just be consistent. We also need to be on target.
Precisely. It's like the difference between a clock that's consistently 5 minutes fast and a clock that tells the correct time. Consistency is important, but accuracy is ultimately what we're striving for.
I'm starting to see how all these concepts, accuracy, precision, significant figures, error analysis, all fit together to paint a more complete picture of our data. It's not just about collecting numbers, it's about understanding what those numbers mean and how confident we can be in the story they're telling.
Exactly. Data analysis is like detective work. We're piecing together clues, looking for patterns, and trying to reconstruct what really happened in our experiments. And just like a good detective, we need to be meticulous, observant, and always questioning our assumptions.
Wow, we've covered so much ground in this deep dive. From beakers to burettes, from titrations to centrifuges, and from safety protocols to the nuances of data analysis, it's been quite a journey.
It has been a whirlwind tour of the chemistry lab. And remember, this was just a starting point for your own explorations and discoveries. There's a whole universe of fascinating phenomena waiting to be uncovered. And with a little curiosity and a healthy dose of safety consciousness, there's no limit to what you can achieve.
So for all of you listeners out there, whether you're seasoned lab veterans or just starting your chemistry adventures, remember this. Keep asking questions, stay curious, and never stop exploring. And if you ever find yourself unsure about a procedure or unsure about safety protocols, don't hesitate to ask for help, because in the world of chemistry, as in life, sometimes the most important discoveries come from knowing when to ask for directions. Thanks for diving in with us. We'll see you next time on The Deep Dive, where we'll unravel another fascinating topic and empower you with knowledge.